I am Sachitrakar. Welcome to Cars Physics. This is my second lecture on kinematics. In first lecture, we have discussed about rest, motion and frame of reference. Okay, we are continuing motion in a straight line. This is lecture 2 and we will first discuss on different types of motion. Okay, usually motions are classified into three categories: one-dimensional motion, two-dimensional motion and three-dimensional motion. Let's discuss first from one-dimensional motion. Okay, if a body either moves along x-axis or moves along y-axis or moves along z-axis, okay, then it is one-dimensional motion. So one-dimensional motion is essentially motion in a straight line. Okay, this is fundamental thought. Then two-dimensional motion. Okay, two-dimensional motion means motion on a plane. Okay, I have shown here. This is x-axis, this is y-axis, and this is z-axis in space. So this plane is x, y plane, and this plane is x, z plane. Okay, and this plane is y, z plane. Okay, if a body moves on a plane, either on x, y plane or on x, z plane or on y, z plane, then it is two-dimensional motion. Okay, there are so many examples of two-dimensional motion. Let's discuss. Okay, first example is projectile motion. We'll study it. It is in our scope. Projectile motion and circular motion are two-dimensional motion. Okay, suppose a body is thrown from ground with velocity u along this direction. This is horizontal line, means parallel to the surface of earth. Okay, making an angle theta with horizontal line, a body is thrown in upward direction. Okay, then obviously you have seen it in your day-to-day life. If a body is thrown like this, or on an open field, if you kick a football like this, you just kick the football, making an angle theta with ground or with horizontal, you have seen it that the ball or the body moves along a curved path. Okay, let this line which is parallel to surface of earth, we do take along x-axis, and the perpendicular to the surface of earth means the vertical line, let y-axis. This is parallel to surface of earth, horizontal line. This is perpendicular to surface of earth, means vertical line. Okay, when the body is thrown along this direction, let instantaneous time is 0 and this is origin. Okay, value of x is 0 and value of y is 0. The coordinates of origin are 0, 0. The body moves like this along this curved path. Okay, this plane is xy plane. This plane is xy plane. The body moves like this. Let at any instant, let time is t, the body reached at point P. Okay, to reach at point P, the body has covered this much of distance along x-axis. Let this distance is x1, and moves along y-axis this much of distance. Let this is y1. Since coordinates of origin are taken as 0, 0, then coordinates of point P are x1, y1. Okay, so when the body moves on a plane, the value of x changes and value of y also changes. If this is another point Q, okay, here the coordinates may be, let this distance is x2 and this height is y2. So coordinates are x2, y2 and so on. So as the body moves on, the value of x and y go on changing. So here the body moves on a plane, x coordinate changes, y coordinate changes. So this is example of two-dimensional motion. Similarly, you may cite another example, circular motion. Suppose a body is moving along a circular path. Okay, you have done it. If you tie a stone by a thread and whirl it in horizontal circle like this, then the body will move along a circular path. Let we start revolving it from this point. Okay, when the body reaches at this point, to reach at this point, this is distance travel along x-axis and this is distance travel along y-axis. So, as the body moves on, the value of x changes and value of y is also changes. So, this is also two-dimensional motion or motion on a plane. We'll discuss all this in brief. Okay. Then comes three-dimensional motion. While considering two-dimensional motion, we may consider any two coordinates, x coordinate, y coordinate, or y coordinate, z coordinate, or x coordinate, z coordinate. But this is three-dimensional motion, means in three-dimensional motion, we will use all these three coordinates, means x coordinate, y coordinate, and z coordinate, means the space coordinate, as we have discussed in Cartesian coordinate system. Okay, so three-dimensional motion. We have to use all these coordinates. Best example of three-dimensional motion. Let a kite is moving in air. Okay, flying in air. Okay. Another best example, the motion of gas particles. Motion of gas particles in space move in all possible directions, means gas particles move randomly in all possible directions. Those are three-dimensional motion. So these are basic idea about types of motion. Okay. Then we may classify again the motion into different types. Let's discuss all these types of motion. Okay. Number one, linear motion, or this is also called as rectilinear motion. Okay, linear motion or rectilinear motion. See students, linear, the word comes from line. Okay, linear motion, if a body moves along a straight line, then it is called as linear motion or rectilinear motion. Okay. Next type of motion, these are only fundamental discussions. Next type of motion is translatory motion, or it is also called as translational motion. What is this type? Translational motion is the type of motion in which a body covers equal distance in equal interval of time. Let's see. Suppose a body is moving along x-axis. Initially, the body starts its motion from this point. Let the central portion of the body is at position A on the ground. It moves along x-axis. Okay. It reaches at another position. Let this position is B. Let time taken by the body to move from this position to this position is T, and distance covered by the body is S. Okay. In next interval of time T, if the body reaches at this position, let this position is C, then the body also has covered the same distance S. Okay. If a body covers equal distance S and S in equal interval of time T and T, then the body is said to be in translatory motion. Then another point under translatory motion. When a body moves or executes translatory motion, then the particles of the body also cover equal distance in equal interval of time. Okay. Let's consider this is along x-axis, this is origin. Okay. This is a particle and this is a particle. A body may contain millions of particles. Let's consider two particles of the body. Okay. This particle is initially at a distance x1 from origin, and this particle is at a distance x2 from origin. Okay. Now the body has displaced or moved from position A to position B. Let this particle is A, this particle is B. Then particle A has reached at this point and particle B has reached at this point. Okay. Then initial position of the particle is x1 with respect to origin. Let this position is at a distance x2 from the origin, sorry, x3, and point B or particle B is initially at a distance x2. Let it reaches at a distance x4 from the origin. Then we have to understand that the particle A has travelled this much of distance and particle B travelled this much of distance. Means the particle A has travelled from position x1 to position x3. Let this distance is x1, x3. Particle B has moved from position x2 to position x4. Then let this distance is x2, x4 in time t. Then obviously, according to the principle of translatory motion here, x1, x3 must be equals to x2, x4. Means the particle A has covered the distance x1, x3. Particle B has covered a distance x2, x4. Both the distances are same because body has covered from position A to position B in time t. The particle A covers a distance x1, x3 in time t. Particle B covers a distance x2, x4 in time t. Both the distances same. So the particles of a body must cover same distance in same interval of time when the body executes translatory motion. Okay. Then let's move to another type of motion. This is fundamental idea about translatory motion. And number one, linear or rectilinear motion. Okay. Then number three, curvilinear motion. Curvilinear motion. See students, the word curvilinear comes from curve. If a body moves along a curved path, whatever be the nature of curve, may be circular, may be parabolic, or may be irregular path, any curved path. If a body moves along a curved path, then the motion is called as curvilinear motion. Okay, let's discuss about under curvilinear motion, circular motion and rotational motion. We have already discussed about circular motion. Okay, motion of a body along a circular path is circular motion. Then other definition we will discuss when two-dimensional motion will be studied. Okay, rotational motion. Rotational motion. Let's consider any rigid body, whatever be the shape of the body, rigid body, a solid body. The body may be of spherical shape, may be of cylindrical shape, or may be any irregular shape. Let's consider a solid body, a rigid body. This is the axis, means this line is passing through the center of the body, or in later stage we will know that it is center of mass of the body. Let the body exhibits rotational motion about its own axis. This is axis, the body exhibits rotational motion. As Earth rotates about its own axis, okay, Earth moves around Sun as well as rotates about around its own axis. Similarly, this body is rotating about its own axis. This is rotational motion. Rotational motion is also explained as motion of a system of particles. Okay, this rigid body contains a number of particles in it. Say, this is a particle, this is a particle, this is a particle, this is a particle. So, this body may contain a number of particles. When the body executes rotational motion, different particles move along different circular path. Okay, so the particles means a system of particles in rotational motion execute circular motion. Okay, so this particle, let's consider this particle. This particle moves along a circular path and it is its center. This particle moves along a circular path. This is its center. Similarly, this is a particle moves along circular path, and this is the center. Okay. So here, rotational motion is the type of motion in which a system of particles exhibit circular motion in such a way that centers of all particles lie on a common straight line, which is called as axis of rotation. Okay. Another thing about rotational motion. Okay. When a body is in rotational motion, the different particles travel different distances in same interval of time. Okay. Motion of Earth around its own axis is an example of rotational motion. Okay. Motion of fan. A fan, the blades of fan execute rotational motion. Let's consider one of the blade of the fan. Okay. Say this is one of the blade of the fan. Okay. Fan is rotating blade in anti-clockwise order, and let's consider some points on its blade. Let's consider 4 points. We may consider the particles on the blade or 4 points on the blade. Let the blade has moved to a new position. Okay. This is the new position of the blade. Then this particle has moved to this position. This particle has moved to this position, and so on. Okay. The blade to move from point A to point B, it takes a time t to move from A to B. In this interval of time, the particle, suppose this particle A has moved at a point A dash, this particle B has reached at a point B dash, this particle C has moved at a point C dash, and so on. So when the body exhibits rotational motion, different particles move along different circular path. Okay. Different circular path. But in same interval of time, the distance covered by the particles are different. Okay. So the particles in rotational motion cover different distances in same interval of time. This is characteristics of rotational motion. Okay. Now let's consider some another type of motion. Okay. Number 4, oscillatory motion. Oscillatory motion. It is defined as the to and fro repeated motion about mean position is called as oscillatory motion. Let's consider this is pendulum of a clock. Okay. The pendulum starts its motion from this position, goes to one extreme position, then to another extreme position, and finally back to mean position. Okay. The to and fro, one extreme position, other extreme position. The to and fro repeated motion about mean position is called as oscillatory motion. Okay. Oscillatory motion may be on a horizontal surface, okay, or on a vertical surface. The to and fro repeated motion is called as oscillatory motion. Another related motion to oscillatory motion is vibratory motion. Vibratory motion is also oscillatory motion, but a little difference between them. Okay, the rapid oscillation is called as vibration. Say a body oscillates, goes to one extreme position, then other extreme position, and back to mean position. Let time taken is now 3 seconds. If time taken by the body to execute similar type of motion in an interval of time, say 0.15 seconds, means this is rapid oscillation. Say for example, this is a thin metal plate. I am holding this. Only I will give it a sudden force on it, then it will vibrate. Okay, then it will execute oscillatory motion, but in rapid state. Okay, the rapid oscillation, the to and fro repeated motion about mean position, okay, it's called as vibratory motion if it is rapid. Okay, so these are examples of some types of motion. Okay. Now we will move to parameters of kinematics. In this lecture 2, I will discuss about 3 parameters. Okay. In next lecture, I will do only problems. I will inform you at the end of my class. Okay. Different parameters or only parameters of kinematics. Parameters of kinematics are also called as variables in kinematics. The variables. Variable means or parameter means taking those terms will express kinematics. Kinematics deals with motion. To express motion, we need these terms or parameters or the variables. Okay. Those parameters are: number 1, position. Number 2, distance. Number 3, displacement. Number 4, speed. Number 5, velocity. Number 6, acceleration. Number 7, jerk or jolt. We will discuss all these parameters in detail, okay, so that we can understand the explanation of kinematics well, and we can approach all the theories related to motion very easily. Then we will apply all our understandings into solving the problems. Okay, this is our motto. Okay, let's start discussion on these parameters. Okay, the first parameter is position. Okay, let's discuss about position. What is position? Okay, position. The first parameter is position. Position. What do you mean by position? Position is location. Position is location where a body or an object or a person is placed. Okay. It is location with respect to reference point or with respect to origin. Okay. In past lecture, I have discussed the state of rest or motion depends upon the state of observer and frame of reference, and the observer always relates the position with respect to reference point, means with respect to origin. Okay. Then position. The fundamental discussions about position. If one asks me, what is your position? What is my position? I am in my classroom. This is my position. If I now, after some time, reached in market, then market is my position. Okay. When I return to my home, home is my position. Plus position changes. Okay. Position changes. So position is location. Position requires, to express position, what we require? We require how far it is, how far an object is, or how far a body is, or how far a person is. Means we have to measure that distance, how far it is. Then another thing is direction. Thus position matters direction. Okay. Distance with direction. Distance is magnitude with direction. So position is a vector. Position is expressed in terms of position vector. Okay, we have already discussed it in my first lecture. Okay, suppose a point or an object or a body is in space. Okay, this is z-axis in space, an object is in space. We have to show its position with respect to origin. Then coordinates of origin are 0, 0, 0. This is the point P. I am representing here the point P. The coordinates of point P means point P is at a distance x along x-axis from the origin, at a distance y with respect to origin, and at a distance z with respect to origin along z-axis. Okay. Then coordinates of point P are x, y, z, and the position vector means position of this object or a point with respect to origin, okay, is determined by this position vector. Okay, we have to measure what is length of this position vector, means distance means magnitude. Then arrow mark shows direction of position with respect to origin. Okay, all these things can be given by position vector r. Okay, expression of r as we have discussed, xi cap plus yj cap plus zk cap in terms of unit vectors, and magnitude is square root of x square plus y square plus z square. Then accordingly we can calculate angle made by the position vector with x-axis, with y-axis, or with z-axis. Okay. In vector you have studied. This is about position. Position depends upon origin. Position depends upon reference point. Position vector changes or position changes as it is a vector which either change in magnitude. If magnitude changes, means this length of position vector changes, then position changes, or due to change in direction. If direction changes, then also position changes. Okay, position depends upon origin. Okay, suppose one person is observing from origin O with respect to him the point P. The coordinates of point P are x1, y1, z1, and here the expression of position vector is x1 i cap, y1 j cap, and z1 k cap. Let this is r1. Okay, and writing expression of r1 again, x1 i cap plus y1 j cap plus z1 k cap with respect to observer at origin O. Okay, let another observer looks the point P or determines the position of P with respect to another origin. Let this origin O dash, this is x-axis, let's take x dash, this is y-axis, y dash, and this is z-axis, z dash. Okay, so position or point P with respect to O dash, the origin. Let's take R2. See, origin changes, position vector changes. Position vector was R1 with respect to origin O. Position vector is R2 with respect to origin O dash. Okay, so if position of origin changes, then position vector changes. Okay, what's my position now? Someone say you are along east and at a distance 500 meters. Suppose I am standing on an open field. Someone say me you are at a distance 200 meters along west. It depends upon the point of observation. And someone may say you are along east. Okay. So all these things means determination of location depends upon observation and the state of observer also from origin. So this is all about position, and this idea you have already got in lecture 1. Okay, then next parameter, number 2 parameter is speed, distance. What is distance? Distance is actual path traveled by a body irrespective of direction. Okay. In other words, we may define distance. Distance is actual path length covered by a body irrespective of direction. So the definition says distance has no particular direction or distance has no definite direction. It's irrespective of direction. So distance is basically path length or length of path. We can measure the length of path. Means the nature of path, whatever may be. Okay. It is the actual path traveled by a body, irrespective of direction. So obviously, distance is a scalar quantity as it is irrespective of direction. Say a body moves from position A to position B along this path. Okay, this is the actual path traveled by the body. To know how much distance is traveled by the body, we have to measure total length of path. Okay, if the body, another body starting from A, travels along this type of curved path, then to measure distance or to know magnitude of distance, we have to measure the whole length of path. Okay, or if a body moves from A to B along a straight line, then this is also distance. Okay, so overall what we have discussed, distance is actual path traveled by the body, whatever be the nature of path, maybe curved path or maybe straight line. We have to measure the actual path length. Okay, so this discussion also shows us distance is path dependent. Means we have to measure total path length. So distance is path dependent. Okay, distance is scalar, distance is path dependent. Also, we can conclude that distance is always positive. Why? Because it has no specified direction. So distance is always positive. Distance can never be zero for a moving body. For a moving body, distance can never be zero. It always increases for a moving body. Okay, all these things again we will discuss when we compare between displacement and distance. Okay, then third parameter, displacement. Displacement is the shortest path from initial to final position. Okay, this is initial point A, this is final point B. Okay, a body may move along this semicircular path or may move along a curved path, whatever be the path followed by the body. But displacement is the shortest path directed from initial to final position. Okay, so direction of displacement is from initial to final point. So displacement has a specified direction. So displacement is a vector quantity. Okay, if a body actually moved along this path from A to B, then displacement is along the straight line directly directed from A to B. Okay, so whatever be the path followed by the body, displacement is always along a straight line directed from initial to final position. Okay, so displacement is independent of path. What we discussed, whatever be the path followed by the body, okay, displacement doesn't depend upon path length. So displacement is independent of path. Okay, it is path independent, but distance is path dependent. Okay, so units of distance and displacement are same. Units of distance and displacement in MKS meter, in CGS centimeter, and in FPS foot. Okay, for longer distance we use kilometer in our regular practice. Okay, for longer distance. So dimensional formula: distance has only length, or displacement is measured in length, though it is shortest distance. So both are units of length. Then dimension: mass to the power 0, length 1, time to the power 0. So these are units and dimensions of distance as well as displacement. Then displacement in other form means to attempt problems. Okay, displacement is change in position vector. Displacement is change in position vector. Okay, let's clarify how displacement is change in position vector. Okay, let's consider Cartesian coordinates. This is origin, this is x-axis, this is y-axis, and this is z-axis in space. Okay, this is origin. Coordinates of origin are 0, 0, 0. If we observe position in space, we use Cartesian space coordinates, 3 coordinates, x, y, and z coordinate. If we observe the the position or displacement on a plane, then we may use Cartesian planes, means either xy plane or yz plane or zx plane. The plane on which the position or displacement occurs. Okay. Let this is a point P. This is position of a body at point P. Then position vector to point P is directed from origin or from reference point. Okay. Let coordinates of point P are x1, y1, z1, and this is position vector r1. Then r1 vector is equal to x vector plus y vector plus z vector, or in terms of unit vector, x1, y1, z1, x1 I cap plus y1 j cap plus z1 k cap. This is expression for position vector of point P. Let the body move to another point Q along this path, means along a curve. But displacement is always along a straight line, so displacement is PQ. Let this displacement PQ is S. Then position vector of point Q, let coordinates of point Q are x2, y2, z2, and position vector is r2. In similar way, we can give expression of position vector of point Q with respect to origin as x2 I cap plus y2 j cap plus z2 k cap. Okay. Thus, displacement vector is PQ, okay, directed from P to Q, and it is S vector, displacement vector. See students, from the triangle OPQ, okay, we'll apply triangle law of vector addition. According to triangle law of vector addition, if two vectors can be represented in magnitude and direction by the two sides of a triangle taken in same order, then third side of the triangle taken in opposite order represents magnitude and direction of resultant vector. From triangle OPQ, see, OP vector and PQ vector are in same order, means in clockwise order, but OQ, the third side, is in anti-clockwise order. So according to triangle law, OP vector plus PQ vector is equal to OQ vector. Okay. Then OP, R1, PQ is displacement vector, S, OQ is R2. Then displacement vector is R2 vector minus R1 vector. This is displacement. So displacement is defined as change in position vector. Initially position vector is R1, and for final point Q, position vector is R2. Then change in position vector means R2 vector minus R1 vector is equal to displacement. Okay. Then total expression for displacement vector. Okay. Displacement vector. In place of R2, we can write x2 I cap plus y2 j cap plus z2 k cap minus, in place of R1, the expression of R1, x1 I cap plus y1 j cap plus z1 k cap. So final expression x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. Okay, this is expression of position vector. Okay, suppose we are considering the displacement on xy plane, then you may put here z2 0, z1 0, because the motion is on xy plane, so z1 0, z2 is 0. Okay. Accordingly, you can put the respective coordinates. Okay. Then magnitude of displacement vector, square root of x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. Okay. You may use it while solving problems for displacement vector, and we will practice. Okay. So this is about displacement. Okay. Then in today's class, means in lesson 2, my discussion is up to displacement. Now we'll compare between distance and displacement. Okay. Distance and displacement. Already we have discussed the points under distance and displacement. Now just comparison, distance and displacement. Distance is actual path or length of path traveled by a body. Okay. Displacement is the shortest path between from initial to final position. Okay. It is actual path, it is shortest path directed from initial to final position. Okay. Distance is path dependent. The actual path means path dependent. Displacement is independent of path, means path independent. Displacement is shortest path, whatever be the path may be. Displacement is along a straight line directed from initial to final position, so displacement is path independent. Okay. Number 3, this is number 2. Distance is scalar, it is irrespective of direction, and displacement is vector because displacement matters direction. Okay. So scalar and vector. Number 4, distance is always positive. Well, moving body, distance is always positive. Then about displacement, may be positive or may be negative. Displacement has a particular direction. So usually initial direction is taken as positive. Okay. Suppose a body moved 100 meter along east, then this is initial direction. So this displacement is plus 100 meter. If he returns back to the starting point in opposite direction, then the displacement is minus 100 meter. Okay. So usually initial direction is taken as positive and opposite to initial direction is taken as negative, or vice versa. Okay. It is convention. Okay. Since we may fix the direction, the initial direction we will take positive and vice versa. Okay. So for distance, number 5, distance can never be 0. Distance can never be 0. Distance always increases for a moving body. Displacement may be 0. Displacement may be 0. Say for example, this is a square field. Okay. A, B, C, D. And each side is let 40 meter. A body starts from A, reaches at B, then moves from B to C, then moves from C to D, then moves from D to A. Means starts from A, again returns back to position A. Then here, distance is, under distance is total path length 40 plus 40 plus 40 plus 40. Okay. So distance is 160 meters. But displacement is 0. Okay. Because this is initial position and a return back again to initial position, means A is initial position, A is final position. So the shortest path between initial and final position is 0. So displacement is 0. Okay. Distance can never be 0. Sum of all these paths. Okay. So for a curved path, let's consider another example. Suppose a body moves along a curved path from A to B. This is actual path. But displacement is the straight line from A to B. So if a body moves along a curved path, then distance is more than the magnitude of displacement. Okay. Distance is more than the magnitude of displacement if a body moves along a curved path, because this is actual path. So this is displacement means shortest path. So actual path is more than the shortest path, means distance is more than magnitude of displacement if a body moves along a curved path. For curved path. Let a body starts from A and moves along a straight line and reaches at B. So if a body moves along a straight line, actually moves along a straight line, then this length is distance. Also, this length is magnitude of displacement. So if a body moves along a straight line, for straight line, distance is equal to magnitude of displacement. So for a curved path, distance is more than magnitude of displacement. For a straight line, if a body moves along a straight line actually, then distance is equal to magnitude of displacement. So our final output, if we compare the magnitudes, then distance is greater than the magnitude of displacement if a body moves along a curved path. Distance is equal to magnitude of displacement if a body moves along a straight line. So distance may be greater than or equals to the magnitude of displacement. So obviously we can say distance can never be less than magnitude of displacement. Now, the numerical ratio of distance to displacement. The numerical ratio of distance to displacement is either greater than or equals to 1. Distance is greater than or equals to magnitude of displacement. So, ratio of distance to magnitude of displacement is greater than or equals to 1. Okay. This class is only the theoretical class. Okay. I have tried my best to explain the theoretical concepts up to our discussion is up to displacement, position, distance and displacement. In my lecture 3, I will discuss only problems. In lecture 3, we will discuss only problems on distance and displacement. So, in lecture 3, problems on distance and displacement. Okay, but before that, before ending this lecture 2, I like to advise you, go through trigonometric formulae and algebraic formulae and also fundamental formula on differentiation and integration. Okay, get prepared. Thank you all.